Hi, Madan.
Meet.
This is Shubhamai.
Sure, man. I'm here. It looks okay. Can you hear me okay?
Yeah, I think you're clearly
Okay.
audible.
Okay. Um, right. Let me just, so there's still some time. I'll just mute it on my end. Do you want to check anything here from my side?
I think your sound is quite fine, and
Okay. Do you want to see the slideshow just to be sure?
we can quickly do a test
Yeah,
whether
let's
it
do
is
that.
visible.
Yeah, let's do that.
Yeah, to me it looks perfect. No problem.
Okay, this is now full screen and everything, so there shouldn't be any issue.
Yeah, and I think you can just click the height there, which is in the lower middle part.
Yeah.
Yeah,
Okay.
yeah, yeah,
I'll do it as soon as we start. Okay.
yeah, yeah, yeah,
So I'll just stop share now for now. Okay.
yeah, yeah.
Okay. So I'll just step away, but I'll be back in a minute or two. If you need
Yeah,
anything,
sure.
you have my WhatsApp.
হ্যাঁ স্যার আপনি কি আছেন মিটিংয়ে? আমি তো আপনাকে একটু অ্যালফাবেটিক্যাল অর্ডারে খুঁজে পাচ্ছি না সেই জন্য। মানে আপনি কি নিজের নামে আছেন না অন্য কোনো নামে আছেন? হ্যাঁ কিন্তু জিতে আপনার নাম পাচ্ছি না সেই জন্য আমি চিন্তায় পড়ে গেছি আর কি। হ্যাঁ জয়েনে ক্লিক করুন মানে হ্যাঁ আপনি এসে গেছেন স্যার। হ্যাঁ
Good afternoon, sir.
হ্যালো তুমি 2 নম্বর স্ট্রিমটা ছিলে তো? হ্যাঁ কৃষ্ণা দিয়ে একটা ফ্রেশ স্ট্রিম স্টার্ট করার চেষ্টা করেছিলেন। হ্যাঁ তো তাতে লিঙ্কটা পাল্টে গেছে। তো এখন আমার তো সব মেলগুলো সবাইকে পাঠিয়ে দিয়েছি। এখন নতুন করে আবার মেলগুলো পাঠানো সম্ভব নয়। তুমি প্রথম লিঙ্কটা দিয়ে চলে যাও, সৌরভ যেটায় আছে।
देखते रहो।
আছে আমাকে? হ্যালো, আছে?
হ্যাঁ স্যার শোনা যাচ্ছে আপনাকে।
আচ্ছা আচ্ছা, ঠিক আছে।
স্যার একটু অপেক্ষা করতে হবে, আমরা 3:30 থেকে ঠিক আরম্ভ
হ্যাঁ হ্যাঁ
করব।
ঠিক আছে, ওকে, কোনো অসুবিধা নেই।
আমার তো সুবিধা নেই, আমার তো এস বলে আছে।
না না, তুমি ক্যামেরার সামনে দাঁড়ালে তো তোমার দেখা যাবে।
হ্যাঁ, সেটা আগের দিন যখন করলাম তখন হচ্ছিল, পরের দিন তো দিন
তুমি এরা বলছি যে আমি সেটিং এ নেই।
স্ট্রিমটায় কিছু একটা প্রবলেম হচ্ছে।
প্রবলেম লেগেই থাকবে অনলাইন ক্লাসে। 3 ঘন্টা 4 ঘন্টা করে সকলে 10 ঘন্টা
ধর ওরা লাগে দেখো চালিয়ে রেখে দেবে, ওদের সঙ্গে একটা একটু কথা বলবো।
সেটাও তো ওরা পাচ্ছে না, ও দেখতে পারমিট করতে হবে, তা আমি তাকে খাই।
কি পারবেন করতে হবে?
হ্যালো, কোথায় পাঠিয়েছেন বলুন তো?
ওই যে চ্যাটে।
না, চ্যাটে পাঠিয়ে তো হবে না, কারণ
হ্যাঁ,
অনিকেত দা, সুশীল বাবুর মাইক্রোফোনটা অন আছে, ওইটা থেকে ব্যাকগ্রাউন্ডে চ্যাট আসছে, এটা একটু মানে ওনাকে যদি অফ করতে বলেন। হ্যাঁ হ্যাঁ, উনি অফ করে দিয়েছেন, উনি আবার অন করেছেন।
অফ করতে বলছি।
হ্যাঁ সুশীল বাবু ঠিক আছে, হ্যাঁ সুশীল বাবু ঠিক আছে।
মন্দার আছে, আমরা স্টার্ট করবো।
3:30, এখনো 3 মিনিট বাকি আছে। I think still there are 3 minutes, so we can probably wait for 3 more minutes, or 2 more minutes.
মন্দার এসে গেছে?
হ্যাঁ, he is there.
আচ্ছা, তাহলে আমি ওকে, বিফোর উই বিগিন shall we request everyone to may I request everyone to switch off your turn off your microphones and your video, please, to allow the speaker greater bandwidth. Please turn off your microphone and your camera. Okay. Welcome everybody to our first webinar in Vidyasagar College Physics Department. I will not like to keep you waiting, so I'll just hand over the microphone to Dr. Sanchari Goswami, who will conduct the meeting from now on. Thank you. Sanchari, please.
Welcome everyone to this webinar. Today I would like to first welcome you all on behalf of the Physics Department, Vidyasagar College. I would like to invite our Principal Sir, Dr. Gautam Kundu, to say a few words for us and inaugurate the webinar.
Okay, thank you, Sanchari. Now, it gives me great pleasure that in the wake of such a pandemic situation which is persisting still today, that is the COVID-19, and subsequently other calamities which are taking place, like the flood and the last night, the happening of the plane crash, It is not everything is actually wrong over here, because every gloomy situations have a silver lining, or a silver cloud is there. So today, such a silver lining is the presence of a speaker, the very renowned Professor Mandar Madhukar Deshmukh. Well, it gives me a great pleasure to welcome Professor Deshmukh to our college. Our college is one of the most oldest among various other colleges, being the first of its type to be run by a native in Asia. Now, today we are stepping into the 200th birth anniversary of our founder member. So it gives me pride that at this particular juncture, the physics department and the IQAC in collaboration has been able to organize such a webinar where a particular speaker of such repute has been invited. So we welcome Professor Deshmukh once again. Professor Deshmukh has done his BTech in engineering, engineering physics from IIT Bombay in 1996. Later, he joined Cornell University under Professor Dan Ralph to do his PhD in 2002. Then he moved on to Harvard University for his postdoctoral fellowship and worked on molecular electronics and microscopic superconductivity. In January 2006, he returned back to India and joined as a faculty member in TIFR, Mumbai, where he is still working as a professor in the department. He has supervised a number of scholars for their PhD work, the postdoctoral work, and also various undergraduate research scholars in his illustrious career. He is also interested equally to interact with young students. This is a thing which actually shows his greatness, because the young audience who are present today would surely benefit through his lecture, and they are waiting eagerly to hear from him and get enriched. And where such a personality goes, the awards also follows him, and he has been awarded a number of awards, and the most illustrious one being the Bhatnagar Award, which he received in 2015. He is also a fellow of the Indian Academy of Sciences. A various number of research papers has been published by him in very reputed journals. Many of our students may not be knowing those journals. Let me say a few of them, such as Nature Nanotechnology, Nano Letters, Applied Physics Letters, Nature Communications. He has even written a book on probing magnetism at the nanometer scale. Well, we are really indebted to him that such a huge academician, which he is, has given his consent today to come over here. And there are two other areas which I've come to learn that he is also interested. One is his love for sports, and he has been a runner. Of course, he is a runner, no doubt, a long distance runner, and he is also interested in cycling and trekking. So he must have trekked a lot in various places. I don't know. I would have liked to meet him personally to know all these things. And his other love is for animals. He has a number of cats, which his daughter happily looks after. So, well, sir, we are really indebted to you that you have given us the consent to deliver the lecture on electronic properties of 2D crystals. Thank you, sir, once again. And over to Sanchari.
Hello.
Thank you very much, sir.
হ্যাঁ বলো
Now,
এই
may I
স্ট্রিমটা কিছু
request
আসে
all
না
of you to
এটা কিছু
kindly
আসে না
mute your microphones
তা
and
না
off your
আমার
switch off your
কম্পিউটার থেকে
videos
একটা স্ট্রিম হতে সমস্যা হচ্ছে
during
কৃষ্ণাদি
the
স্ট্রিমটা চলে
talk.
যেতে হবে কৃষ্ণাদি
So for
স্ট্রিমটা
the
মনে কাজ
next
করছে
part, we are now going to the next part, that is the talk. And now I would like to
হ্যাঁ আমারটা কাজ
ask
করছে না
Shubhomoy,
আমারটা
Dr.
কাজ করছে না
Shubhomoy Ghotok
আমারটা কাজ
from
করছে
our
না
department to conduct the next
তোমরা
part.
অন্যটাই চলে যাও অন্যটাই চলে যাও
Shubhomoy.
একটাই কাজ করছে একটাই কাজ করছে
Yeah, Sajadi, thank you. Let me just briefly introduce the field where Professor Mandar Deshmukh has been working for several years, and I think that will help our students to know more about him. So, am I audible clearly?
Yes, yes.
Hello? Okay.
Yes, you are audible.
Yeah, it's good.
So
Shubhama, it's good.
As a principal investigator, Professor Deshmukh has been exploring multiple areas in physics, particularly with low-dimensional materials. And some of the examples of the field which he's working is micro and nano electromechanical resonators with one-dimensional nanowires and two-dimensional materials. Magnetotransport in one-dimensional nanowires and two-dimensional graphene, topological insulator, Dirac and Weyl semimetals. Quantum Hall and broken symmetry states in graphene field effect transistor. Coupling of mechanical modes and quantum Hall states in graphene resonator. Electromechanical modes in superconducting two-dimensional BISO crystal. And metal insulator transition and thermal properties such as thermal expansion and bolometric responses of 1D and 2D materials. Very recently, he is also investigating the fascinating role of 2D materials in cavity optomechanics, cavity magnonics, cavity quantum electrodynamics, and vanictronics. I think with this, I would like to request all the participants to welcome Professor Mandar Deshmukh in this webinar.
Okay. Thank you very much, Professor Kundu and all the faculty members of this very illustrious college, Vidyasagar College. It has history which is very incredible. I learned about it, and the first college in India which was run by Indians, where Indians taught. It's kind of an amazing history, and it's goes back much further than any other educational institution in India. So I feel great, privileged to be part of this webinar here. So thank you, Professor Kundu, and all the colleagues here, Shubhamay Ghatak and Aniket. I know them from past for several years. So thank you very much for having me here. Let me get started with my talk. So I love questions. Okay, so is there an audio problem? I got a message saying there's an audio problem. Can you hear me okay?
Yeah,
Shubhama, can you hear me okay?
Yeah.
Clearly.
Yeah.
It's
Okay,
clear.
all right. Okay, all right, fine. All right, so let me get started with my talk. I love questions, so I would suggest that you save the questions to the end. That might make the webinar more smoothly. I want to answer every question that you have. So even if it's the most simple question you think, please do not hesitate to ask me at the end. That's sort of the most exciting part for me in a talk, is to interact and answer all the questions that students have. Okay, so thank you very much, and let me get started. So I want to tell you today about electronic properties of 2D crystals. While I get started, I want to acknowledge the very important support that we get from different agencies of the Government of India, which is Department of Atomic Energy and Department of Science and Technology. And these are, indirectly, they are basically arms of the the common public which supports this kind of research activities. So I'm really grateful for the support over the last several years. So I don't do the work alone. I am going to give you a glimpse of the research that we do. But the people who really make the research possible are my collaborators, students, postdoc, scientific staff at TIFR. So these are presently the people in the group. You might, some of you might notice Shubhamay, who was working with us until the end of last year. So, scientific work is possible, cutting edge work is possible because of collaborations, and I have lots of collaborators in TIFR, rest of India, as well as some outside as well. So I want to acknowledge their contributions in work. So what do? Our goal in our research group is to look at physics of electronic flow, mechanics, at a length scale of nanometer, order of a nanometer, where we are talking about either electrons flowing through something which is only a few atoms wide or thick, and I'll elaborate a little bit more. So I'm just going to give you a kind of a photo album view of what we do. I will not talk about all of this. So we look at superconductivity, induced superconductivity in graphene by connecting graphene to superconductors, which are called Josephson junctions. We look at superconductivity in very thin atomic crystals, which I will talk towards the end of my talk. We look at magnetism in crystals and ask what is the nature of information that can be carried by magnons, which are the unit of magnetic excitation. Something that's close to my heart is looking at mechanics. So imagine you have a tabla or a drum, which is only one atom, and its diameter is only about 3 micrometers. We have been over the last years looking at vibrations of this one atom thick tabla, and essentially trying to study the frontier of mechanics. And something that is kind of at the center of a lot of our activities is looking at quantum transport, which is basically looking at electrons going through small confined regions where quantum mechanics or the signatures of quantum mechanics starts to play a very important role in understanding what actually is happening. So this is kind of a bird's eye view of what we do. I encourage you to look at our webpage. It has links to all our publications, and some of them are freely accessible. So this gives you a big picture idea. So I'm going to include some of these in today's talk, but I'm not going to talk about everything because it then becomes too much and hard to convey a story. So let me get started. So this is my rough outline for today's talk, which I expect to finish in an hour. I'm going to start by asking some rhetorical question. One hears this, one has heard in either media or in your college. You might have heard from your friends, 2D material or 1D. So I want to ask, who defines what is a 2D or a 1D material? What's the criteria? That will provide me a starting point to talk about some of the things that we work on. So I'll provide a broad introduction about what is interesting and exciting. So I'll talk about graphene, what's interesting. Graphene is one atom thick graphite. And then I'll talk about few layers of graphene, some new developments in this field. I'll try to give you a glimpse of it. And then towards the end, I'll talk briefly about 2D superconductors, which are only few atom thick, and what's interesting. Okay, so that's roughly my outline. I'll show it at a few different places to tell you where we are in the whole talk. Okay, so let's get started. So if I ask a question, what is a 2D material? The answer to that is you have to qualify it. It's not a blanket answer. So if I say I'm talking about a 2D material, the question I should be asked is, are you talking about its electronic property or its optical property or its magnetic property? Because what is two-dimensional for electronic properties may actually not be two-dimensional for optical or magnetic properties. So you have to ask what particular physics or science that you're exploring, then you can make a qualification that it's a two-dimensional material. So just saying that it's only this thick, so it's two-dimensional, is actually not an accurate answer. So let's say into the electronic property, which is the focus of what I will talk about today. For electronic property, de Broglie wavelength, which is sort of the extent of the wave function of electron, or in case of metals or semiconductors, it's the Fermi wavelength. These are two quantities are the same thing. They determine what the dimensionality is. Okay, so if you want to ask, for electronic property, what's the dimension of the system, you really have to say what are the dimensions of the material relative to its de Broglie wavelength or Fermi wavelength. So if I confine, or if I make a material thinner than the de Broglie wavelength or the Fermi wavelength, then I suppress that dimension. So if we live in a three-dimensional world, but let's say I kind of flatten a piece of gold or any other metal, and I flatten it, and I flatten it thinner than the de Broglie wavelength, which is typically for metals, typical metals, it's the order of a angstrom, a fraction of a nanometer. Then that dimension becomes reduced, and it's called a two-dimension. Then let's say I try to make a wire out of it, and I squeeze the second dimension also smaller than the Fermi wavelength, then I can make it a one-dimensional material. And often if you confine it tighter in all the three dimensions, people will use a terminology which is called a zero dimension. So these are nomenclatures, but what's important to keep at the back of your mind is what's the scientific reason for calling something which has a reduced dimensionality. Okay. So that's sort of the big picture. So what we look at is a wide variety of 2D materials, and one of them which had caught the fascination of the community, the scientific community, and also has to some extent caught the fascination of, I hope, some of you young students, is a material called graphene. It's basically a material that you have actually made many times. If you've used a pencil in your academic sort of growth from school, let me just take a sip of water. Then you have already made this material many times in your school. And the way it works is, if you have graphite and you peel off layers of graphite, the one atom limit of graphite is graphene, and it's a honeycomb structure which has carbon atoms all at the corners, and to some of you who might have taken some basic course in solid state physics, there's a classification scheme of crystals which is called uses Bravais lattice. So in the two-dimensional world, the way one makes this crystal allows us to say that this is in itself a honeycomb lattice, is not a Bravais lattice, but you start with a triangular lattice, which is this green atoms, and then for centroid of every green atom, you kind of place an orange site, allows you to create that honeycomb structure. So one sort of technical way is you start with a 2-carbon atom basis, which is A and B. So these are chemically the same chemical species, carbon atom at these two locations, but they are distinct. And this is at the heart of the physics associated with graphene in some sense. And the way to distinguish between the site green and orange is that if you ask the environment of B is different from that of A, although it might look like they're the same. On right side of B, there is no atom. And on the left side of A, there is no atom. So these two sites are kind of have some symmetry related to it, but they're not the same. And that's actually one of the themes of physics, is that symmetry, some property of the material, determines what happens in its properties. So whenever we want to look at electronic properties of solids, we want to ask what is the relationship between energy and momentum of electrons in any material. That's sort of what essentially the essence of solid state physics is. And in case of graphene, one sees that you will get to set of electronic states, or which are called bands. This is called the conduction band, this is the valence band, and they actually touch each other at exactly 6 points. So because they touch each other, this material is called a semi-metal, not a semiconductor. And its semi-metal is because its density of electrons is low compared to typical metals, but there is no gap in its electronic spectrum. So, and if one zooms in, one sees that this part of the conduction band, which is relevant to understanding its property, and the valence band, and this blue shaded region is the Fermi energy, they are basically mirror images of each other across this blue plane. This is the Fermi energy, this is the conduction band, and they are conical. Okay, so this fact that they are conical leads to some simple conclusions. Is that the energy momentum relationship of the electrons close to the Fermi energy is linear, which is slightly unusual. Graphene is not the only material where this happens, but it's a prominent example. So what does it mean? It means that these electrons behave differently than much of solid state physics, and I'll show you a couple of comparative slides in the next few slides. So what that basically means is that this point, which is called the Dirac point, and the nomenclature will become clear in a minute, is the meeting point of the conduction band and the valence band, and the Fermi energy is basically the highest level up to which the electronic states are filled. And if I ask how many electrons I can fill at different energy, it gives me a quantity which is called density of states. It's a little bit sort of technical name, but what it really measures is how many possibilities are there for putting electrons at every energy. And what I really get an answer is that at this energy, which is the sort of the energy right here, Fermi energy, or the Dirac point, my number of charge carriers is actually vanishingly small. So at this point, I have very few number of electrons available for to carry current. And one of the power of these experiments, which is experimental physics, is that you want more knobs, and so one can actually make transistors out of this kind of materials, wide class of materials. These transistors are no different in principle from the field effect transistors that you might have studied in electronics course, MOSFETs, or any kind of FET. These are field effect transistors. So using these materials, and I'll show you examples of this as we go along, you can actually make a 3-terminal transistor where the graphene forms the channel, and you have another electrode which is a gate, which is across this, which is the dark blue metal is the gate, and this light bluish green is an insulator or a dielectric. And so what one does in this sort of 3-terminal device, one is source drain, is as I apply a gate voltage, I can put electrons in this channel, just like think of this as a one-plate graphene as my plate of a capacitor. Then if this gate is a metal, then I can, applying a voltage, I can either induce electrons here or remove electrons depending on the sign of the voltage. And then I can measure the transport. So what this geometry allows you to do is kind of continuously tune the charge carriers on demand. You just change the voltage and you'll be able to change the density of charge carriers by moving this Fermi energy, this blue plane that you see here, which is exemplified by this black line. So as you apply some voltage, let's say negative, you move this plane down. Or if you apply positive voltage, you move this plane up in the same device. And that's really kind of one of the exciting knobs, experimental knobs that one gets in this system. So once you have this, we can make kind of lots of interesting studies, and this was one of the major accomplishment of the Nobel Prize winner Andrei Gaiman, Kosten Osolov. They actually peeled off one layer of graphite and made an electrical device. Okay, so we're gonna see how it's done. But let's just, before we go there, let's just quickly revise what we know, from our everyday existence or rest of solid state physics. We know that the energy momentum relationship of most of the things in our everyday life and most of solid state physics, the energy momentum relationship is quadratic. So I have energy is quadratically related to the momentum in almost all of solid state physics except for a little bit. Then on the other hand, the extreme is relativistic, but ultra-relativistic, say, particle physics, which will look at physics of particles moving in accelerators, or moving anyway close to, whichever way close to the velocity of light. Then the equation, if they're massless, then you describe them by this equation, which is called the massless equation, where c is the velocity of light. These are two limits. This is what one sees typically in solid state physics and what one sees in high energy physics. Turns out that the relationship that I showed you for the case of graphene exactly mimics that of the relativistic particles, with a very important distinction. This velocity v is not the velocity c as in case of ultra-relativistic massless particles, but it is some other velocity vf, which is about 300 times slower than the velocity of light. It just turns out that the structure of the governing equation, which technically one calls the Hamiltonian, has the same structure as that of Dirac equation. I won't go into the details here, but if somebody has a question, we can talk about it. So the electrons in graphene, monolayer graphene, one layer of graphite, behave as if they are relativistic particles. Okay, so I want to be very, very clear so that there is no misconception. They behave as if they are relativistic particles. They are not relativistic. So the governing equations are the same, except the prefactor is not velocity of light. Okay, so that sort of brings us to put the physics of graphene in context, and that's one of the reasons many of the physicists are interested in it, because you can explore some things which you cannot actually explore in particle accelerators. So now this was a very important knob when first people kind of discovered this in 2005, and since then there has been a rapid growth. Now, symmetry of the crystal, it plays an important role in determining its properties. So I already told you graphene's equation is described by this, and it has a honeycomb lattice with carbon atom at each point in the two sites that I told you. Whereas if you think of boron nitride, which is a cousin of graphene, it has no carbon, but alternating boron and nitrogen. So as a pair, boron and nitrogen are on either side of carbon in the periodic table. So as a pair, they are isoelectronic as two carbon atoms. But one main difference that happens is that once you have different atoms at the two neighboring sides, you break one important symmetry, which is called the inversion symmetry. Inversion symmetry is if you have a system and you say k going to minus k or r going to minus r, you invert across a symmetry point. Then in case of graphene, the inversion symmetry is preserved, whereas in case of boron and boron nitride, which is a cousin material, that inversion symmetry is not there. So if pink side does not go to blue side, so that symmetry is not preserved, and actually that leads to the fact that this material breaking of this simple symmetry, that I don't have carbon everywhere, and I break the inversion symmetry, makes this a very good insulator. So this simple fact comes out of the its property that some simple symmetry property of the crystal is kind of destroyed. And boron nitride is a very convenient material in this system I will talk about. So the take-home message from this slide is that simple symmetry property of crystals, which some of you may already know, determines important electronic properties. So now I've given you a kind of pedagogical background. Let me just give you a quick sort of dive into experiments. How does one make these kind of crystals in your experiments? So, sorry, let me just do that. So this is a video from YouTube, which I put a link here, but you'll find many on this. I just exemplify this. One of the power of this experimental field is to do this high quality physics. All you need is a tape, a sellotape in India, and a crystal of graphite, and you peel it off. And you peel it off, and you will basically see that you may actually be able to make one atom thick graphite. You don't need any sophisticated instruments or anything. It just needs hard work and skill. So you peel it many, many times. Okay, so that's what she's says in this. And then you kind of peel off this tape. So and you put it on a piece of silicon. And at some place you basically leave randomly. Okay, so this cannot be predicted, but randomly you will deposit 1 atom thick, 2 atom thick, 3, 4, 5. Then you'll have to search for them. And that's actually what the Nobel Prize winners did. So this is not sort of the technique by which okay, so you don't actually need a very sophisticated optical microscope to do it. I encourage some of the students to try doing this, in maybe in your experiment with the permission of your professor. So some simple physics allows you to see things which are only 1 atom thick. So this is an example from our lab. Where you see thick crystal. This is a very thick crystal. It looks mirror-like. So some of you may know that pieces of graphite will have mirror finish. So they'll be very shiny. But as you make it thin, you will see different colors. And the change in the colors, this physics is no different from the physics of seeing, this is monsoon time. If you see, near an auto stand or a bus stand, you'll see puddles of water, and then you'll see this rainbow color film floating on top of water. That's thin film interference. And essentially, this change in the color is this exactly same physics. And this was realized by Andrei Geim and Novoselov, and that speeded up the progress of making devices. So interference allows you to, even though this is only 1 atom thick, it provides enough phase shift to be able to be seen using a simple optical microscope. Okay, I'm not talking about a fancy optical microscope. So the mathematics of it, I won't go into, is if you have a sort of a 1 atom thick membrane at certain wavelength of light, which is 600 nanometers wavelength, which is sort of the close to the middle of the visible range. And if you use an appropriate substrate, which is basically this thickness of this blue layer. So this gray region is silicon, this blue is silicon oxide. So if you use 300 nanometers, then exactly in the middle of the visible range, you'll get a peak in the contrast. So you'll be able to see it using a simple optical microscope. So the simple realization of using interference to see something which is 1 atom thick was quite handy experimental trick, and it was basically a smart use of the right kind of thickness of this oxide. Again, you can make graphene on any substrate you like by lots of different techniques, but if you choose the dielectric environment, it becomes easier to see it. So how do I know? Just because I see something which is thin doesn't mean it's monolayer or bilayer or trilayer. Turns out that we have to be grateful to Sir C.V. Raman, who actually discovered this physics way back, which is the Raman effect, which is basically you shine a light and you look at the light that gets scattered back out of that material, and the light that gets scattered off can have different components. One is energy less than the original light, same as the energy as the incident light, or actually more than the energy of the incident light. So these are details of the Raman processes. But what it does is it exchanges energy with the excitations inside the material. So in this case, most solids will have vibrations or phonons. So the phonons will take up some of the energy in this process. And that phonons are characteristic. They are kind of fingerprint of that material. Okay, so if I measure this light carefully, I will actually find out a unique fingerprint, which is unique for 1 atom thick. It's totally quite different for 2 atom thick or 3 atom thick. So people have used Raman spectroscopy. It's one of the most powerful tools to identify whether you have 1 atom thick or 2 atom thick or 3 atom thick. And this not just holds for graphene, but it holds for lots of other materials. So Raman effect is the foundation of a lot of scientific experiments and technologies in chemical sensing. So we have, we have to feel gratitude towards Sir C.V. Raman for this amazing discovery. And so if you look at the spectrum, you can actually identify which is watertight evidence that this is 1 atom thick. Not just that, you can identify some defects inside the material as well. Okay, so Raman scattering is a way for me to know for sure. So once we see this, we actually test and confirm that it is 1 atom thick by essentially Raman scattering. So now we have this. So now I told you our in our lab, the bread and butter experiments is to make kind of devices, electronic devices. To give you an idea, this triangle is about roughly about 25 micrometers by 25 micrometers triangle, and it's 1 atom thick. Okay, so this is actually not a very difficult length scale. We use techniques from semiconductor industry to make wires or electrical connections to it. I'm going to show you a simple example here just to sort of make you aware of it. And so the process simply works by putting some plastic, essentially copper polymer, on top and exposing it to a beam of electrons or photons, and that kind of changes the property. It actually doesn't kind of remove it, but it changes the properties, and it can be removed by using a liquid. And then once you have it, you can deposit metal on graphene or whatever else that you like, and the metal goes through. So this idea is actually something very straightforward. If you have used a stencil to do anything in your school career, this is a way of making stencil but using polymers. This is what you've seen is the basics of lithography, which is a complex process by which all the integrated circuits are made. And so at the end, once we put the electrical connections on it, by the process that I just told you, you have an electrical device where I can now apply voltage and measure current. Okay. So that's really the essence of what the kind of measurements that one can do. So now, briefly in the next couple of slides, just to give you a flavor, one of the kind of measurements that we do is studying the quantum Hall effect. Okay, so everybody knows about Hall effect, and quantum Hall effect is a kind of sort of quantum version of this classical Hall effect. But before that, let's just think about what happens to the electronic states. This is energy, and this are y-axis here is the density of states. So in case of graphene, this is how the spectrum looks. In case of any other material, typically the density of states is constant over energy in 2 dimensions. But the essential point here is that there are electronic states at every energy. Essentially, there are no gaps in this electronic spectrum. For a typical metal or metal-like system, there are no gaps in the spectrum. Now, as you apply magnetic field, even before we talked about any classical Hall effect, the electrons start to go around in circles. You may know from basic electrostatics, if they have a velocity and a magnetic field is applied perpendicular to it, the electron will see a Lorentz force. And they will try to go around in circles. That's sort of the semi-classical way of looking at it. But what you can extend that idea a little bit further, and you can think of quantum mechanical version of it. If you quantize those circular orbits using same ideas as one uses in Bohr atom calculation, simple-minded Bohr atom calculation, then you actually get that the metal starts to actually look more like an insulator or like an atomic system. So the energy states are no longer continuous as you apply magnetic field, but they actually become discrete, much like an atomic system, but they have some spread. I won't go too much into detail, but the take-home message is that they actually, the energy levels inside the metal or graphene start to behave like energy levels. These are called Landau levels. So application of a large magnetic field makes these energy levels well separated from each other, and this material no longer resembles the starting material, which is a metal. Okay. It actually becomes something like an insulator. And that's one of the main dramatic changes that happens when you start studying quantum Hall effect, is that these energy levels become well separated from each other. And so what really happens is that you get these energy levels, which are called the Landau levels. And as you tune the density of electrons in the system, you can occupy one energy level or one Landau level or two available to you. As I told you earlier, you have a gate electrode which you can use to tune the density of electrons. And that actually, this orange region is actually a very good insulator because it doesn't have any electrons near the Fermi energy. And this is a very good insulator, whereas the two strips that you see at the edges, these are the only two places where electrons can flow. Same on the other side. And if you change the number of Landau levels, you have one on one side and another side. This simple realization of quantum Hall physics that people figured out, shortly after the discovery of integer quantum Hall in the 80s, is now at the heart of a kind of a revolution in condensed matter physics, that the bulk properties of a material can be something, but the boundary properties of a material can be topological, which are related to what's happening here. I won't go too much into detail, but quantum Hall effect is in some sense the mother phase where a lot of this interesting physics was studied, and now a lot of, you might have heard of terms like topological insulator. I won't talk about it today, but they are all can be connected to the physics of quantum Hall. So what really one sees in quantum Hall is that if I measure the Hall conductivity, which is basically inverse of the Hall resistance, it will show steps Okay, and these steps are unique, that they are actually just a function of the charge of the electron and Planck's constant. They don't depend on anything else. No material parameter is involved. So you do it in graphene or some other material, they will be quantized in units of E square over H, integral multiples of E square over H. And a practical application of this is that the SI units system that we use was based on some complicated standards, some located in Paris. Now they're defining some arm of that SI system is now defined in units of standard of resistance, which is based on this quantum Hall. This is E square over H has dimensions of conductance. Inverse of that is resistance. So this is now a meteorological standard for measuring the system of units. So we look at the physics of quantum Hall system. I'm going to give you a flavor of what we do. So the kind of measurements that we do are often at low temperatures, which are can be down to 1 Kelvin or even lower, down to about 20 millikelvin. And we want to reduce all other degrees of freedom for the system, and primarily we want to reduce the effect of any phonons, which is the vibrational degree of freedom. At low temperature, they're completely gone. So what we experimentally measure is a resistance as a function of parameters like the gate voltage. This is the gate voltage is the magnetic field, and we plot numbers as in colors scale primarily to help visualize large data sets. But you can think of mathematically, this is a large matrix with probably a dimension of something like 1000 by 500 or something, where and these are just conductance measured, and these sharp lines are Landau levels, which are the consequence of the quantum Hall effect. And if I measure the transfer Hall conductivity, you will see steps in it. You'll see plateaus. These are plateaus which quantize at integral multiples of these. Why they occur in units of 4 or units of 2 or units of 1 depends on the underlying physics, and I indicated to you the symmetry of the system. So in case of graphene, there are some symmetries or degeneracies or internal degeneracy of the system which can be broken. For example, spin of the electron I didn't really talk about, but spin up and spin down has 2 states. And in case of graphene, there are another 2 degrees of freedom, which are called valley degrees of freedom. I won't go into detail, but under right conditions, that's symmetries can be lifted, and you see these steps in units of 2 or steps of 4 or 1. And this is something that we have been exploring. So often these experiments require measurements at very low temperatures, large magnetic fields, which is sort of what we do in our lab. Okay, so just to orient you, I have maybe another 20 minutes, 25 minutes to go in the talk, or maybe 20 minutes. Maybe one of the organizers can just remind me again. But this is what I had shown you earlier. I told you what is a 2D material. I told you about graphene, which is kind of the ultimate example of two-dimensional material, because it's only 1 atom thick. You cannot make something thinner than 1 atom. Okay, so and it automatically also satisfies the requirement that the thickness is smaller than the Fermi wavelength. So now I'm going to shift gears and give you another example of the physics that we have been studying, which is, once you understand graphene, few layers of graphene, there have been some revolutionary developments in the last 2 years. I'll kind of give you a flavor of it. So everybody, or at least some of you students might have heard of kind of the picture which is called the chronic penny model, which is, imagine in the basic quantum mechanics, you have a potential in which you have electrons, and then you create a barrier, and then you look at the incident wave packet, look at the reflection or the transmission. But now imagine you have an array of these, or a repeated periodic structure. Okay. Now this, and you look at the electrons going through this system. This is the most primitive way to describe electrons moving in any solid, whether one-dimensional, two-dimensional, or three-dimensional. Because when the electrons are going over around the positively charged nuclei, they feel a potential, and then away from it, they don't feel. So this is a simplistic description, of course. And so this periodic sort of change in the potential and the electron going through is the basis of how one thinks about electrons moving in a solid. Okay, so the starting point is often studied in courses called the chronic Penny model, and once people found semiconductors and other materials, they wanted to tailor to their requirement some electronic property, because if you have a material, let's say silicon, it doesn't have all the desirable properties. So, or gallium arsenide, which is a cousin of silicon made using gallium and arsenic. So, one way to engineer or tailor desirable properties was to make regions of different semiconductor alternating. And that actually is a way to realize this periodic lattice. And this periodicity does the job of reflecting the electronic waves or scattering them, and gives rise to new band gaps or in semiconductors. So this has been well known and well studied, and some pioneering devices were developed in the late 70s by Su and also Esaki, where, imagine now you have, this is a cross section, this image is a cross section of, that's a piece of material, and you have alternating regions of material A, material B, material A, material B, and the spacing is about 10 nanometers. And this led to a completely different material. This composite material altogether acts like a different material whose properties are different from the starting materials. Not radically, but they are allow you to tailor by tuning this periodicity and choice. And that's what is called a superlattice. It's called, the terminology for it is engineering the band structure. When you want to make interesting electronic devices or systems, you tailor their properties. And so this idea is in general very powerful, that if I have a solid and I create these kind of alternating regions, whether it's a semiconductor or a metal, I may actually realize some new properties. And that's actually the same revolution that happened in the 70s, is in a weird way coming to two-dimensional materials that I told you, but happening not, this material is a three-dimensional material, but it happens in two dimensions, and I'm going to give you an example of it. And the way to make it is, if you have a sheet of graphene, which is, let's say, this purple colored, and then you have another layer of graphene on top of it, rotated it by, let's say, a small angle, 1 degree or 2 degrees. Now what happens is that you have electrons in graphene and then another layer on top, and you will see, you might have noticed this, if you are looking through some mesh in your windows, and you might see the same physics. As you rotate one mesh relative to another, you will see a beating pattern. It's kind of an interference in space. And that interference pattern is basically, at a much longer length than the atomic spacing. So the atomic spacing is the smallest honeycomb lattice. This is about 10 times or 20 times that. Okay. So now for the electrons, this beating pattern is a way of making this superlattice structure, but now in its plane. So this material doesn't exist in the third dimension, but it exists only in two dimension, in the plane of the screen. So the electron wave function, or the electron waves, now will see this different environment here and different environment at these parts, and that really creates a kind of a superlattice kind of structure. And there is a large amount of tunability that you can actually tune this periodicity, and I'm going to show you a video quickly. So people have in the last 2 years found this as a very revolutionary way to engineer electronic properties of materials, particularly graphene. So the easiest way is kind of explained by this sort of video, which I have not made, but it's made by somebody at ETH Zurich, but it's a nice animation. So as you rotate relatively on a long scale, you see this kind of moire. These are called moire. But if you zoom in, you'll see this pattern picture that I showed you. So this moire length spacing depends on the relative rotation angle. So the more you rotate, the smaller the spacing becomes, and as you rotate less, let's say 1 degree or less, the length scale can be order of nanometer. And this is a very powerful way to engineer electronics. So I told you that it's a very powerful way, but let me give you a consequence of this. So there was a really path-breaking experiments done in roughly in 2018, where people found 2 layers of graphite rotated with respect to each other by roughly 1.1 degree. It actually starts to superconduct. So there is everything made of carbon, no metal, which is sort of our conventional understanding. People found that because of this relative rotation and the resulting band structure, electronic band change, under certain conditions, this graphite, just pure carbon, behaves like a superconductor. And this has been subsequently verified by groups elsewhere. And it has led to kind of a furious work in this field to try to understand the physics, not just the superconductivity and some other ideas of topology that I won't talk about today. So this is the consequence of rotating 2 layers relative to each other, and we have been also working in this area. So just to give you a more direct feel for it, so people develop their own experimental tricks. So the question is, if I have 2 layers if I have arbitrary 2 layers of 1 atom thick material, how do I align them precisely to 1.1 degree? Because this physics happens at precise angles, and it's actually experimentally very hard to get crystals which are aligned. So one simple way is you start with, and this is what we do in our lab to make these kind of devices, we start with a single crystal of graphite, or graphene in this case, and we cut it, literally like this kind of a scalpel. And you cut it with a very fine, essentially tapered fiber, scalpel, which we make ourselves. And this is an example of 1 atom thick graphene. And after cutting it, it becomes 2 pieces. Now, because I cut this crystal, I know exactly these 2 crystals are, because they arose from the same crystal, they are perfectly aligned. So then what we do is we start with these 2 crystals. I will pick 1 crystal up, okay, and I leave the other crystal behind. Then I rotate the crystal that is left behind on another surface by a precise angle of choice, let's say 1 degree. Then I bring these 2 crystals in contact, and then they like to stick to each other. So now at the end, these 2 crystals are rotated relative to each other by a precise angle theta that you desired. So that's sort of the standard way to make these kind of devices. And once you make these kind of layers, these are called twisted bilayer graphene, twisted double bilayer graphene, which is what we have been focusing on. We can make complex devices. To give you a scale bar, this is about 20 micron. These are lots of electrical connections for different electrical signals. Just a scale bar that I love is that roughly a human hair's diameter is about 100 micrometers. It's a scale that I love. So you can think of this width, complete width, as the diameter of a typical human hair. And in the schematic of these kind of devices is that they in the one that we have been studying is 2 layers of graphite. We studied twisted double bilayer. Okay, 2 layers of graphene and 2 layers of graphene, but these 2 units are rotated relative to each other, and they're rotated by a precise angle to study the physics. And so when we measure the electronic properties, we have different experimental knobs. Again, this is, you can think of this as experimentally measured data at I think a temperature of about 300 millikelvin, so 0.3 Kelvin, where the color indicates a value of resistance. So again, this is a large data set. So to visualize it, we map the number into a color. But what we experimentally measure is apply voltage, measure current, kind of always measure resistance in these kind of experiments. And so we have 2 experimental controls, which we can independently control the density of electrons, and we can also apply a perpendicular electric field. So we can apply an electric field in this direction. And that tunes its electronic properties. So electric field is a very important knob. It makes, in this particular material, at this point, it behaves as if it's a metal, but if at the same point, if you start applying electric field in this direction, it actually starts to behave more like a semiconductor. Okay. So the easiest way to think of this system is in terms of one electronic band, collection of states. Then as you apply electric field, this band or electronic state splits into 2. It starts becoming more like a semiconductor in this point. And this ability to tune these material from a metal to a semiconductor by applying electric fields, involving these bands. These are called flat bands which I won't have too much time to go into details, but if somebody is really curious, they can ask me in the questions in the next couple of minutes. So these flat bands are where interesting properties take place, where you can realize superconductors or ferromagnets. And the reason why these are interesting is because in these bands, the kinetic energy, they are flat. The kinetic energy is completely quenched. So it's the way to think about it is velocity of charge carriers or electrons is extremely small. So they are very sensitive to feeling each other's interaction. Okay. Whereas if they're moving around a lot, they don't feel each other's presence. So superconductivity or magnetism, all these underlying physical phenomena, they arise from this basic idea that they come from electrons interacting or talking to each other. And that's what gives rise to this physics of superconductivity or magnetism. And that's why these bands, which are completely flat, have generated a lot of interest in the scientific community. So I now show you the last segment of what I promised is that I told you about a graphene, monolayer graphene. There are some interesting discoveries that people are working on, and including us, working on few layers of graphene. I gave you an example of twisted graphene, which is graphene rotated relative to the other. And the essence of doing that rotation is that it creates another periodicity or kind of potential that tailors the properties of electrons. So I go to the last part in the next couple of minutes, and then I'll kind of briefly summarize, and I look forward to the questions. So one system that we have been working on in the last several years is a superconductor, which is a cousin of graphene. It's a complicated chemical formula. I'll show you the crystal structure. Its acronym is BISCO. Okay, bismuth, strontium, calcium, copper oxide. And it has a very intriguing structure of bismuth oxide plane. So there's a repetitive plane of bismuth and oxygen arranged, then a plane of strontium oxygen, then there is an important plane of copper and oxygen. So think of these as layers of, sort of really one atom thick layer placed on top of another, and so on. And this composite thing is one unit is called, with a particular periodicity, is called BISCO. And so this is a high temperature superconductor. It's a superconductivity, critical temperature is 85 Kelvin. These are called high temperature superconductors because the transition temperature is large. And this class of superconductors, which are with a transition temperature higher than liquid nitrogen temperature, are of great interest because liquid nitrogen is easy to make and it's not expensive. Okay, so of course we want, one of the major aims of a large amount of solid state research is to realize a superconductor at room temperature, which is 300 Kelvin. This is a goal where a lot of people are working on, but it has been a hard goal. So the next step is to have superconductors and electronics based on superconductors which are above liquid nitrogen temperature, so that critical temperature, so that you can use liquid nitrogen to realize properties. So we have been doing experiments. This is a difficult material to work with because the superconductivity in this material is now accepted to arise from these copper and oxygen plane. This plane which is the reason for the superconductivity. Other planes play some role, but this plane of copper and oxygen plane plays sort of the critical role. But what people have found that this material is extremely sensitive to oxygen going away. So in the last couple of years, people have tried to using the same kind of process or some variants of it to make this superconductor down to its half unit cell. So instead of having many copper oxide planes, people have now made superconductor using one copper oxide plane, two copper oxide plane. Okay, so they have demonstrated that the superconductivity still exists. So many such layers of copper oxygen just make the superconductor more robust, but the basic superconductivity arises from these, and they have shown that down to few units per cell BISCO one can realize superconductivity. Not just that, one can actually tune the superconductivity by applying essentially a gate by tuning the density of charge carriers inside, and that's really very powerful for making new kind of devices. Again, this technology and this idea was not possible in the has maybe more than 10 years ago. People have worked hard. So working with BISCO is much harder than working with graphite or graphene. So we have been working with BISCO, which is a few unit cell, a few nanometers thick, so high TC superconductor, and so it looks like this shadowy area, and then we make electrical connections to it. So our goal in this kind of experiment was to take, so if we have everything superconducting, it's not that exciting. If we are able to tune the superconducting property spatially, some regions we intentionally can make it not superconduct, then that can lead to exciting electronic devices. And that's what's really interesting. Okay, so we have tried to tailor the properties by, we realize while doing experiments that we can tune the property by depositing some chromium, which is a metal which has affinity to the oxygen. So even though the BISCO here is very thin, few atoms thick, putting a little bit of the material on top essentially does local chemistry and results in a kind of change in the material's property by distorting the stoichiometry. So the stoichiometry of different atoms together with oxygen gives the intriguing superconductivity. But by choosing the right metal, one can actually make the superconductivity go away on demand. So if you make a structure like this, then there is no superconductivity across wherever a wire or thin layer of chromium has deposited, but rest of this material still remains superconducting. This is sort of what is illustrated in this orange curve. It remains superconducting, which is outside this region, whereas if I measure across this, there is no superconductivity. And this shows a kind of a powerful way to make a new kind of devices, electronic devices, by controlling superconductivity on a small length scale. This has not been done before. So this gives you a flavor for what we have been working on. So I'm going to quickly summarize my talk. I told you what are 2D materials. I gave you some idea of graphene, some idea about how you can do more interesting and exciting physics with few layers of graphene. And then towards the end, like metals, but you can also tune properties to be superconductors. I didn't go into a lot of detail in each of the topics, primarily because it gets a little bit technical. I want to give you sort of the flavor of the excitement of experimental physics. So I'll stop here, and I'm looking forward to your questions. Thank you very much for your kind attention.
Shubhamoy.
Hello. Yeah, am I audible?
Yeah.
Yeah, thanks a lot to Professor Mandar Deshmukh for his extremely informative, motivational and enjoyable talk. We hope that it has given an introduction to fascinating electronic properties of the nanomaterials and also a glimpse of the current research activities in this field. And with this, I think we'll move into the question and answer session. From my side here, I have one question from Mandar, and this is from Yasha Biswas. So she's asking, are Dirac point and Fermi energy level coincide with each other in graphene? Then what is the physical significance of this?
Okay. All right. So what I might do is I'll use a screen to draw some stuff wherever needed. I see in the chat box there are lots of some are questions and some are probably messages to each other. So let me just the first question. So let me just go back to the slide. Thanks. Okay, so you should be able to see. So let's come back here. So maybe here is simpler. So so this point, let me. So this point is the meeting point is called the Dirac point. Okay, and the Fermi energy is basically an energy which up to which the electronic states are filled. It's not in the pristine graphene, it happens to mid-right. Pristine means sort of undoped, or chemically there are no additional electrons than what carbon atom donates to the lattice. Okay, at that. And under that conditions, the Fermi energy goes right through the Dirac point. So it's precisely at the meeting point of the two cones. But it's not a sort of a very big deal because I can tune the Fermi energy using sort of the experimental devices that I told you. I can actually tune the Fermi energy from here. I can move it here, or I can remove some electrons and I can put it here. So I can tune it precisely. The beauty is that in some experimental systems, you cannot tune the Fermi energy so easily. Whereas in many of the 2D materials, you can actually tune it with a knob like the gate voltage. And so in these experiments, one can align it precisely with the Dirac point on demand. You tell me that I want to. I don't think there is any deep. If I understood the question that Shubhamay said, and you can correct me, is that there's no deep meaning other than in the pristine graphene, because one electron comes from each of the carbon atoms in a pi orbital. It's going to be precisely half filled at this point. Okay. And that's why it happens, because the contribution of electrons from each carbon atom is the same in pristine graphene. If you change that, answers the question. Shubhamay, okay, you can check whether this is a well answer to the question that this person asked.
We can ask Piyasha Vishwa whether she is in Google Meet or she asked from YouTube Live. I think it was from YouTube Live. Then she can probably give a reply and probably get feedback back. And then there is two more questions. One from Rabia Sultana. I think she is in Google Meet and she can directly ask him. Rabia, could you unmute your microphone and ask question to Professor Mandar Desmukh? Thank you. Hello.
Okay.
Is Rabia there?
Yeah, maybe just to save time, maybe I'll just read the question, or maybe Shubhamay, you can do it, so that it gives people time to answer ask questions. The question which says, what is the difference between a 2D material like graphene and a 2D topological insulator? So it's a good question. So as I told you, the physics of quantum Hall effect, where away from the boundary, you have some interesting property, which is an insulating property in the middle, and then towards the boundary, you get a conducting property. In some sense, your 2D topological insulators are close cousins of the quantum Hall state, except that 2D topological insulator does not require a magnetic field. So you can get that physics from some other kind of interaction. So the 2D topological insulator is typically because of spin-orbit interaction, which is the interaction between the spins of electron at an orbital degree of freedom. Graphene is very different from a 2D topological insulator because it has very little spin-orbit interaction. Spin-orbit interaction is a function of the atomic number, and carbon being a very small atomic number, it has kind of minimal spin-orbit interaction. So in the first proposals of Kane and Mealy, who made some really pioneering observations in the field of topological insulators, they started with a structure of graphene and kind of said ad hoc, if there exists strong spin-orbit interaction, you'll get these 2D topological insulators or spin Hall insulators, quantum spin Hall insulators. But in real graphene, there is very small amount of spin-orbit interaction. So graphene is different from 2D topological insulator primarily because it doesn't have spin-orbit interaction. That's the short answer to your question. Okay, then there's another question from Mr. Rajesh Mukherjee, which says, few layer graphene band tailoring by mechanical rotation or anything else. So there are many ways that you can tailor the band properties. I gave you an example of mechanical rotation, but you can engineer them by creating superlattice by using periodic gates also, which does the same thing, a similar thing, but is not as clean a way to make it. So That's the short answer. So I gave you an example of mechanical rotation, but that's not the only way. You can realize it by other. Okay, now there's another question. Shauna Bose, which says, what are the applications of
Shauna Bose.
Yeah. What are the applications of having a material with certain parts of superconductivity? Only can we determine exactly what portions of the material superconducting. Yeah. So, what are the applications? So, there are devices which are called superconducting quantum interference devices, which are called SQUIDs. That's an acronym. That basically has a ring of a superconductor. So let me go back to, I hope you can see the screen. So a typical SQUID has a structure like you have a superconductor everywhere, and it has a weak link. So you will kind of apply some voltage and measure current. All these arms are kind of superconductors. These are called weak links, a region where the superconducting order parameter can twist. Okay, so these SQUIDs are very powerful devices for detecting magnetic fields and different kinds of sensors. And so if you want to make this, you really have to kind of pattern the superconductor. So it's superconducting here and not conducting here. And that's sort of one of the motivations for the kind of experiments we are doing. And in our case, we know precisely where it superconducts and where it doesn't superconduct. In the last example, I'm guessing you were alluding to this, is that underneath chromium, it doesn't superconduct. But everywhere else, it superconducts nicely. So we can actually make some complex geometries using the metal that is deposited on top to realize devices. So as you might sort of realize that kind of interesting devices can be made if you can pattern, sort of spatially pattern, and that's one of the reasons. So there is an abrupt edge between superconductor and non-superconductor, but that's kind of fairly well understood. I mean, there are some details that are quite interesting and different for the case of high DC superconductors, but in general, an abrupt junction between a superconductor and a normal metal is understood. There's interesting physics there. Okay, so we can move to the next question, which is from Rabia Sultana, which says, what was the crystal growth technique used? Okay, this is a good question. So we don't grow crystals, as I explained. We literally, you can buy crystals of graphite. Maybe 10 years ago or more than 10 years ago, you can probably buy it off eBay, which doesn't exist in India anymore, but you could buy those crystals. These are often mined. You can, you get it out of mining. And we buy these crystals. They're essentially natural graphite crystals, and we peel them off. But that is not a scalable way to make industrial graphene. There are processes called CVD, chemical vapor deposition, which allows you to make sheets of graphene, which are basically 10 centimeter by 10 centimeter length. However, they are not as nice crystals for doing the kind of physics experiments that is improving day by day, but it's still not as nice as this field of crystal, primarily because it has some defects, some grain boundaries, or pentagon heptagon defects. So instead of a hexagon everywhere, it has pentagon heptagon, and that creates problems for the electrons to flow. So we use this natural graphite. Okay. somebody's microphone is okay. Somebody's microphone is having a feedback or something. Yeah. Okay. Now there's another question by Subhajit Roy Chaudhary, which says, two bands are touching each other at Dirac point in graphene. Is it possible to make it semiconducting by making a gap of 1 eV by some means? Okay, great question. This is the goal of a semiconductor industry. And one of the reasons people were disappointed in graphene, despite all the hype, is that it doesn't have a band gap. And it's actually very hard to make a band gap. So let me just, this is a very good question. Let me answer that using the slide okay, let me use this slide. Okay, so as you can okay, all right, I hope you can hear me now. There's some feedback from some one person probably. So let me explain this idea. So the fact that graphene is metallic or semi-metal like, that it doesn't have a band gap, arises from this basic symmetry that there is an inversion symmetry across the crystal. Okay, so that if I, at about the center of the top black hexagon, at the center point, if I go make all the lattice points x, which are at x, go to minus x, which means basically inversion here, you get back the same lattice again. Okay, this simple symmetry that the lattice has inversion symmetry guarantees that you will have no band gap. Okay, so the most reliable way to make a band gap in graphene is to break the inversion symmetry, which is to realize a system where there's one chemical species here and another chemical species. So just starting from graphene, you have to figure out a chemistry method or some other material science technique of changing the chemical environment here and not doing it here. It may become possible in future, I cannot say that. But in some way, it's already realized through something like boron nitride, but boron nitride is not, does not satisfy the criteria that you prescribe of band gap of 1 electron volt. Because boron nitride has a band gap of about 6 electron volts, so it's really not a good material for semiconducting devices. But there are other materials which are not using carbon, called molybdenum disulfide, or which are called dichalcogenides, which have formula which is AS2 or ASE2, and they, in some sense, are exactly what you desired in your question. Their crystal structure is 3 atomic layer, but effectively it's like a honeycomb lattice, with this being a different chemical species. So they don't have inversion symmetry, and they have band gap of close to 1 electron volt. So it exists. So to realize the question that you asked, one really has to break the inversion symmetry. There are materials which already do that. To do it in graphene, you really have to chemically functionalize every alternate carbon atom to different chemical species. If that can be done, you will realize what you asked. Okay, I hope that answers your question. So this is one of the reasons why graphene had a lot of excitement, but it doesn't have a band gap, and so it's actually a terrible material for making transistors, because if you make a transistor out of graphene, it's a tap which always keeps on leaking. It's a leaky tap. So it's not a good tap to have in your computer, because it consumes electricity all the time. So to close that tap, you really need something with a band gap, as you asked. Okay, I hope I answered your question. Then there's a next question, which is Arghya Datta. Is it possible to develop a semiconductor by doping of graphene-based materials with So sodium and cesium. So people have studied what you suggest extensively, but just chemical doping only changes the Fermi energy. It moves the Fermi energy up or down. It cannot open up a band gap, and it opening up of a band gap, I told you, in graphene structure, monolayer graphene. In bilayer graphene, if you have 2 layers of graphite, you can open up a band gap. It has a slightly different band structure. You can open up a band gap by applying a perpendicular electric field. Now, in case of graphene, the only way to open up a band gap, or one way is one short way is to break the inversion symmetry of the lattice. Okay. Other way people have explored is to make thin ribbons of it, which is to realize band gaps in the structure because of quantum confinement in one dimension. However, that has not gone very far, to the best of my knowledge. So sodium cesium doping will only tune the density of carriers but not open up a band gap. There is one more question from Rabia Sultana, which is reason behind the signature of quantum transport steps. So those are because of the quantum Hall effect. I did not have time. I mean, I'm sorry to have taken only 2 slides about this topic, but you know, it can itself be a topic of a 1 semester long course, or a 1 hour lecture, quantum Hall effect. But let me just briefly repeat what I said. So these kind of steps in the conductance, you know, Hall conductance, they arise because the electronic spectrum, which is the electronic set of states, are no longer continuous but are discretized. The electronic spectrum, because of the magnetic field, is not like that of a typical metal. And that gives rise to the Hall conductivity increasing in steps. Why it increases in multiples of either 2 or 4, I told you there are degeneracies in the system which determine whether the step is either 2 or 4 or 1. If you lift all the degeneracies of the system, like it happens here, you'll see a step at every E square over H. Here, that degeneracies are not lifted, so you'll see, you know, the steps being either in the multiples of 4 or 2. Okay, I hope that answers the question. Now there's one more question from Samir Sarkar. What was explained was an example with disco. Sorry, Samir Sarkar? Yeah, okay. What was it? What was it? Yeah, go ahead, Shubhaman.
Yeah, so what was explained was an example with visco. I'm eager to know what effect do impurities in such system had. Again, I would like to know how pure was the sample that was studied.
Okay, so it's a good question. So we know that the sample was very pure because just in the same device, just outside the region which is covered with chromium, you get perfect superconductivity of what is expected from visco, which is of about 85 Kelvin. Just under the region where is covered by chrome, the superconductivity is destroyed. So this is kind of like a surface science where you destroy the stoichiometry below the layer. We are not alloying or anything. We just literally depositing on the surface. So you can follow chemistry or any material science, surface deposition or surface doping. The rest of the control material, which is in the same device, the control is in the same device as where we do change the superconducting property. and can be measured simultaneously.
আপনার লিঙ্ক তো
So
পাল্টে
this
গেছে
whole
এবার
crystal of chrome of bisco is there. We measure simultaneously this crystal of bisco. It remains, its properties don't get affected. Whereas here, where we deposit some material just on the surface, no alloying, no bombardment, nothing, the superconducting properties get modified. Okay, so that's sort of the answer to your question. I hope that answers. The next question, Shubhamay.
ওটা লিঙ্কটা তো পাল্টে গেল।
Yeah. So there's a question from Arnav Saha. So he's asking, in symmetry breaking slide in the lab, is there any coexistence of symmetry and symmetry breaking states? If so, can we think about chimera state formation there?
Okay. Can you repeat the question? So I didn't. Can you repeat the question? I didn't understand something that you said.
ওটা নিয়ে কিছু ভাববেন না।
In the symmetry breaking slide, is there any coexistence of symmetry and symmetry broken states? If so, can we think about chimera state formation there?
Okay, so I don't have good understanding of the chimera states. I don't know. I'm not familiar with that terminology, so I won't really be able to address that particular word. But yeah, so there can be states where you can realize things where symmetries are broken and symmetries are not broken. So for example, this particular system is actually precisely 3 layers of graphene. It's called tri-layer graphene. It can actually give rise to kind of a ferromagnet, which is called a quantum Hall ferromagnet, where certain symmetries are broken, like spin symmetry could be broken or valley symmetry can be broken, but the other is preserved. Okay, so it depends on the nature of the electronic interaction which symmetry is broken. So it's certainly possible. So the answer is it's certainly possible.
Yeah, so the next question from Saurabh Rudro, how to change band gap of any material?
Okay, that's a great question. It's not the short answer to that is it's not straightforward, and one has to engineer. There are some strategies. One strategy is alloying. Let's say, gallium arsenide is a cousin of silicon. 3-5 semiconductors, you might have heard of it. Depending on whether you use arsenic or phosphorus and what relative fraction in the alloy, gallium, arsenic, and phosphide, you can realize a wide variety of band gaps depending on the composition of the material. So that's one strategy. The other strategy is strain. Often, if you take a crystal and you stretch it in one direction or compress it, stress it, or compressive stress or tensile stress, the band gap can change in different ways. These are sort of commonly used in semiconductor industry. There are other methods, but these are the most common techniques that I know.
So the next question is from Shubhajit Roy Chaudhary. So he's asking, inversion symmetry breaking will incorporate foreign atoms in graphene to make a band gap. Will this incorporation of foreign atom carbon structure retain all its exciting properties?
If you have foreign, what you call an atom, if they're regularly for electronic properties. So if you have something which is regularly sitting on top of the carbon atom every alternating site, then it's not so bad. I already gave you an example of a molybdenum disulfide which does not have any carbon and in some sense has the same honeycomb structure with this inversion symmetry broken. So sure, you will not get the kind of the Dirac nature, because the moment you open up a gap, you won't get massless Dirac fermions. You get what are called, in terms of massive Dirac fermions. Now, if your question is in terms of device properties like mobility, I think mobility can be a complex material property, and one can engineer it. So now the mobilities of molybdenum disulfide or tungsten diselenide over the last 5-7 years since their initial work have increased quite a bit, and they've become quite respectable, coming close to few hundred centimeters square per volsec, and even some special reports claiming sort of special conditions you can get even higher mobility. So that's already quite a lot for if you really want to replace silicon. Silicon's mobility at room temperature is not that great, but so there are other aspects to it, but it's not such a bad. I mean, if you can regularly do it, it's not such a bad thing. So exciting properties are somewhat in guessing mobility or something. It's possible to realize those properties in other materials. Okay, next question.
The next one is if we see in a high magnetic field, any changes will be observed?
So
it's not very clear.
That's a good question to me. Yeah, so I'll try to answer it the best I can. So I mean, it is also diamagnetic. Graphene, it's graphite has diamagnetic properties associated with it. So you'll see that, but it's not going to explode or anything. If or nothing untoward is surprising is going to happen to the crystal structure. If that's sort of what you're wondering.
So the change in the real space, that's what he tried to mean.
I don't think there will be anything itself. I mean, if you have a free-floating graphite or any diamagnetic material, if you put it in a magnetic field, it's going to kind of get repelled. But I don't really think anything will happen to its crystal structure.
Yeah, I think at this point, I think there is one question here. Comment on the future of graphene-based spintronics.
Yeah, it's
graphene-based. So he is asking comments.
Yeah, so I mean, I think it's an interesting prospect. There are some things which are not nice in graphene. The spin diffuses over large length before dephasing. But it also, because it has low spin-orbit interaction, you can now there are increasingly new ways people are finding to incorporate other materials on top or on locally depositing it or using exchange coupling with a substrate which has large spin-orbit interaction to get that papers. Yeah, so I think it's still an active area of research where people still are exploring. So it has lots of exciting properties for spintronics.
I think at this point, this was the last question from the people who are attending the seminar. And I think with this, we can hand over the mic to Shanchariji. She can take it over. And thanks, Mata, also for patiently answering all the questions
Sure, yeah.
regarding the Google Meet and help you.
Yeah, it's a pleasure. Thank you. Yeah.
Sajid, please.
Yeah. Thanks to Professor Deshmukh once more for such a delightful talk today. May I ask everyone to please unmute yourselves for a digital clap? I think that should be here. May I ask everyone for a digital clap?
Thank you. Thank you.
And please mute yourself once more. So we are really privileged today to have you here, Professor Deshmukh. Thank you once more. And now I would like to ask Professor Shogata Bhattacharya to give the vote of thanks.
Thank you, Sanchari. So now time for vote of thanks. I would start with hope that whenever we go to the class and start teaching pedagogy quantum mechanics, like the superconducting band gap, you also see a gap there. It starts with 1D quantum system and then it suddenly jumps to 3D quantum systems, and the entire world of 2D is missing. So I hope with this topic that is actually much popping up heavily, I hope the 2D world of quantum mechanics
দেওয়া যাচ্ছে না, তাহলে ওখানে লিখে দাও যারা ফিডব্যাক লিখতে চায় ওই vc.physics.webinar@gmail.com এ ওদের লিখতে বলো, আমি ওদের ফিডব্যাক লিঙ্কটা মেল করে দেবো।
Thank Professor Deshmukh for a wonderful talk.
হ্যাঁ, ওখানে মেল করতে বলো, আমি মেল করে দেবো।
And I think it's a very, very commendable job that you have done. So thank you once again from all of us, from the college, from the speaker, the participants, and from everyone. Thank you once again. I would also like to thank the principal of our college who had been a motivating factor and who has guided us through many stages of preparation. Thank you, Professor Gautam Kundu. I would also like to thank the chairman of IQSC, Professor Alok Choudhury, who has been a constant source of inspiration throughout the process, the governing body, and particularly our HOD, Professor Aniket Basu and Professor Shinomoy Water. They have done the yeoman's job of holding up this. This is a stupendous performance. So I would like to take this opportunity to thank them once again. The faculty members of the department, they have also been instrumental. So, and the non-teaching staff and everyone of the college who has made this occasion a success. Then again, I would like to thank the faculties of other colleges and institutions who have joined, participated in this gala occasion and made this program a successful. Last but not the least, the students for whom this lecture is attended, for whom this lecture is meant actually. So if those people who are actually meant to be inspired get inspired by this talk, then only this talk is successful. And if that interest seeps into this research so that they get motivated into doing research in this field, the wonderful world of 2 dimensions, that would be a great job. And we hope to tap into this great source of inspiration, Professor Deshmukh, maybe once in a year, if he can actually make some time for us and give feedback to maybe motivate students. That would be a wonderful job. And I would, the participants who are not only from our college, other colleges, and from abroad. So I would like to take this opportunity to thank them all to make this program a success. Once again, with a heartfelt thank you all who has attended and the speakers and the organizing committee. I would like to conclude this thanks session. Thank you all. So now for Shantari, I guess, also.
I think we can conclude the session now, and we can share the feedback. Okay.
I don't have much to add. I don't think anyone came to listen to me. Okay. I'd like to thank Mandar again. And thanks to everyone who listened. Thank you very much.
And Anikit, I think students probably may ask for the feedback link.
Yes, sir. I'm in the process of posting it.
Our whole arrangement and all these things. So I think we also need to set that feedback link in the YouTube also. I think both the streaming was fully there are almost 100 participants in each of the streams, I think. As I checked very quickly.
Yeah, something went wrong with my stream and Krishna's battery went out in the end. Krishna's
But
computer
at the end,
died.
there was a long question and answer.
Okay. So thank you very much for having me here. I really enjoyed it. I would certainly love to visit sometime in future in person and interact with the students in person. So I will take your leave now if that's okay. Thank you again.
Thanks, Mandar.
Yeah.
Yeah, thank you very much. Yeah, thank you.
Yeah.
Bye.
Yeah. Anikita, is it okay if we also share the feedback link in the email?
Yes, I'm sending them by email.
Yeah, that will be great. Thank you. So then if there is another seminar or webinar somewhere, people can attend there.
Yes.
Your message is very clear here that the feedback link will be sent via email. So if others have any other webinar to join, can probably go and join there and enjoy that.